All right, guys, welcome to lesson 9.2. We're going to give you guys some basic log properties today so that we can learn how to more quickly evaluate logarithmic expressions without having to change them into exponential form. So we're going to try to learn how to think logarithmically today rather than exponentially, just kind of training our mind to think differently. Also, we're going to look at two special types of logarithms known as the common log and the natural log. So let's go ahead and jump in and see what we got here. So first of all, let's talk about some basic log properties. Anytime the base matches this number here, which is called the argument, the answer is going to be 1. And why is that? Because you guys know that if we were to rewrite this in exponential form, you would have this number, which is in this case a, raised to this power, which is 1, equals this number, which is a, and of course a to the first power does equal a. So there's that. So anytime, so now instead of changing it to exponential form like that, we're just going to say, okay, anytime these two things match, the answer is 1. Okay, so we're just going to start training our mind to think logarithmically instead of exponentially. Here's another one. No matter what your base is, anytime there's a 1 here, the answer is 0. Why is that? Because any number to the 0 power equals 1. How about this one here, number 3? Anytime this base number matches this base number in your argument, which also has an exponent, the answer is just going to be whatever the exponent is. Why? Because a to the x power is equal to a to the x power. Okay, here's another one. Now this one is a little bit more difficult to think about in that way, but here's kind of a nice way to think about a lot of these. Like for instance, we've learned that logarithms are the inverse of exponential functions, right? So since they're inverses, that means they're opposites. So in a way, you can kind of think of it like they cancel each other out. So like this cancels this and you're left with x. Well, the same thing applies here. This is an exponent, so these kind of cancel each other out. We have an exponential with a log in it, so they kind of undo each other. And so you end up with the same thing. It's just x. Okay, now I'm not going to prove that one to you, but I'm just going to say anytime you have this situation, so long as this number matches this number, whatever's here, that's the answer. And for property 5, this has no solution. There is no number that you can raise a to in order to get 0. It's impossible. Same thing down here, no solution. If you have a negative number here, there's no way you'll ever get an answer. There is no power that you can ever raise a to in order to get a negative number, assuming that a is positive, and yes, when you're doing logarithms, this number will always have to be a positive. So you can never raise a positive number to any power and get a negative as a result, and therefore that's not possible. So a shorter way of saying this is the argument of a log must be positive. The argument of a log must be positive. So if you ever see a 0 here or a negative number, there's no math that needs to be done. The answer is no solution. All right, so let's go ahead and move on here. We're going to do example 1. We're going to evaluate each one of these logarithms below, and we want to indicate which property, 1, 2, 3, 4, 5, or 6, was used to solve it. All right, so as for number 1 here, I'm noticing that my argument is a 1. And when I look back on this slide over here, that was this one. And what we had there was a 0, right? And so in this case, the answer will be 0, because no matter what the base is, anytime this number is a 1, the answer is 0. And I'm just going to put P2 for property 2. Now, this property is not really called property 2. That's just what I'm arbitrarily calling it. There's not like you're going to see that in a textbook. They don't call that property 2 all the time. That's just what I'm calling it in our notes for today. Okay, but that's property number 2 that I used there. Let's take a look at another one. On number 2, I see that this number matches this number. Look back at your notes. It's property number 1. And on property number 1, what we've discovered is that anytime these two numbers match, the answer is 1. Let's take a look at this one. This one I've got a 0 here. And according to property number 5, if you take a look back at your property number 5, you'll see that there's no solution for such a thing. Logarithms always have to have a positive number here. They can't have a negative. All right, let's take a look at this one. This is the one where it's kind of like this one cancels this one. And so you're going to be left with 4. And that property, I need to look at it because I don't remember what it is at this point. Which one was that? That was property number 3. So anytime you've got these two numbers matching, but this number has a power on it, the answer will be the power. Let's go ahead and take a look at this one here. We've got a negative number, and that means there's no solution, and that's property number 7. And then our last one here. This is the odd one where these two things cancel out, leaving you with whatever's right here. So my final answer will be 5x. And that would be property number, I want to say 4. Oh, I put 7 here. This was supposed to be 6, my bad. So property number 4. All right. So instead of changing each one of these things into exponential form to find the answers, I just have a list of properties now that make getting the answers a little bit quicker. Okay. And that's what the goal is today, so that we don't have to translate this into the language of exponents anymore, but now we can just learn how to start thinking logarithmically. All right. So here's a student practice. Go ahead and pause the video here. I would like you guys to write down what the answer is and also list which property you used. When you unpause the video, you will see the solution. All right, so here are the solutions, and then here's the properties I used to come to those conclusions. All right, let's go ahead and move on here. So how to think logarithmically. When you see an expression like this, what you want to think is, what number would I have to raise this value here to in order to get this number? To what power would I have to raise A in order to get B? Whatever that answer is, that's your answer. So let's go ahead and apply this kind of logarithmic thinking to get our answers. So here, what power would you raise 2 to in order to get 8? To what power would you raise 2 in order to get 8? Well, the answer is 3. How about this one? To what power would you raise 5 in order to get 25? Well, that would be 2. 5 to the second power is 25. All right, next one. To what power would you raise 6 to in order to get 1/6? That's a weird one. Now, if you guys might remember, though, 6 to the negative 1 power is 1/6, right? So, to what power would I raise 6 to get 1/6? The answer is negative 1. Now, you guys might be thinking, Mr. Bailey, you said there can't be negatives. Well, there can't be a negative here or here, but you can have an answer that's negative. That is possible. All right, next one. To what power would you raise 3 in order to get the square root of 3? Well, perhaps you recall that the square root of 3 is actually just 3 raised to the 1/2 power, right? So what power would I have to raise 3 to get square root of 3? The answer is 1/2. All right, so this is how we can start solving logarithms by thinking logarithmically. Let's go ahead and have you guys try one of these. So let's try to find the solutions to these problems by just thinking logarithmically. When you unpause the video, you'll see the solution. All right, so here you go. To what power would you have to raise 3 to in order to get 9? The answer is 2. 3 to the second power is 9. To what power would you have to raise 7 to get 1/7? The answer is negative 1. 7 to the negative 1 power is 1/7. To what power would you have to raise 7 to in order to get 1/49? Well, 49 is just 7 squared, right? So if 1/49 is the same thing as 1/7 squared, well, that's just the same thing as 7 to the negative 2 power. So 7 to what power would give you 1/49? The answer is negative 2. All right, last one. To what power would you have to raise 6 to in order to get the cube root of 6? Well, the answer would be 1/3. A cube root can be rewritten as a 1/3 power. All right, so there's that. Now, these problems can get a little bit more complicated, okay? So, like if I were to ask you this, what power would you raise 3 to get the square root of 27? That's going to be a head scratcher. So for a lot of these, what we're going to end up doing first is we're going to rewrite the arguments. And that's what I'm going to do for these two problems here, is I'm going to rewrite the arguments. And what do I mean by that? We're going to change radicals into exponents. We don't want fractions. And finally, we want matching bases. So I'll show you what I mean there. It's a lot like what we did before when we were solving exponential equations a little while back. So let's start off with the first one there. Log base 3 of the square root of 27. Well, first of all, we don't like radicals, right? So I want to get rid of that. I'm going to rewrite it as log base 3 of 27 to the 1/2 power. Okay. Now this says no fractions. Now I'm not talking about fractions in the exponent. That's okay. When I say no fractions, I mean this number can't be a fraction. We're not there right now, so we don't have to worry about that one. But we do want matching bases. This number has a base of 3. This number does not. So we're going to rewrite it. 27 can be rewritten as 3 to the 3rd power. Now that we've done that, we can multiply these together and get 3 over 2. And now we can use property number, I believe it's 3, to just ignore these two things, and our answer is 3 over 2. Okay, so the goal here is to get this number to match this number. So we can use property 3 and just cancel these things out and have this. So how did I do that? I changed the radical into a power, and then I made my bases match. Let's take a look at another one. Okay, once again, I don't like square roots, right? So I'm going to rewrite that as 1 over 2 to the 1/2 power. Now, that took care of changing radicals. We also don't want fractions. Now, like I said, exponents that are fractions are okay. I don't have a problem with that. The problem is I don't want this to be a fraction, and we need to fix that. That can be fixed simply by writing it as 2 and making the exponent negative. I don't want this to be on the bottom, so I move it to the top. And when you do that, it changes the exponent into a negative. That is an exponent rule. And now, lo and behold, we have the bases matching already. That's kind of nice. So these just cancel out, and we've got our answer, -1/2. Okay. So that's how you're going to solve some of the more complicated ones. Now, if you wanted to just go ahead and, solve these exponentially, you could basically take something like this. You can make it equal x, and then you can just do 3 to the x power equals the square root of 27 and solve it like we did back in Unit 8. But we're trying to think more logarithmically today. Now, as for this last one here, this one is actually strange. And so you're not going to be able to get this base to match this. You can get 9 to match 3, but we're not allowed to change this number. Okay, you can't change this to 3 squared. So we're only allowed to change this number. So that makes things a little bit more complicated and strange. So for these types of problems where you can't get this number to match this, I would say just solve it by rewriting it as an exponential problem. Okay, so in other words, we're not using shortcuts anymore. We're not thinking logarithmically anymore for these types of problems. We're just going to go ahead and think of it as an exponential problem. So for instance, log base 9 of 3. I can't change 3 into 9. And so what I'm going to do is I'm going to say, okay, this equals x. And now I'm going to change it to an exponential function. 9 to the x power equals 3. Okay, now we're going to solve this in pretty much the same way that we did Unit 8. We're going to make the bases match. So now that it's an exponential form, I can change this. It's going to be 3 squared. We can multiply those. And this one has a power of 1, so I can just cross these off, set those exponents equal, and divide. So these ones are what I would say a little more complicated problems. And we've kind of looked at two types now. Okay, so we've looked at kinds that have fractions and square roots. For those, I'd say just get rid of the fractions and square roots and make the bases match. We've also saw ones like this where you're not able to get the argument to be this number. And so my advice is in those ones, just change them to exponential form and solve it like we did in Unit 8. So here's a slide for you guys. I'm going to pause the video here and give it a try. And when you unpause it, you'll see the solutions. So number 1 is the problem where I would encourage you just to change it to exponential form, because there's no way you're going to be able to write 9 as a base of 27. So changing it to exponential form, we would have 27 to the x power equals 9. Then we would get the bases to match. They would match with a base of 3. 27 is 3 cubed, 9 is 3 squared. Set the exponents equal and solve. Okay, let's take a look at number 2. Now, number 2, we want to rewrite this radical as a 1/3 power. And then we also don't want it to be in the denominator, so we're going to move it to the top with a negative power now. And then finally, the log b and the b cancel, leaving us with negative 1/3. Now, number 3 was just me testing you a little bit, making you think a little bit. We have done things kind of like this in previous lessons, but not today. And so I just want to make you think. So if you didn't get it, don't feel too bad, but here's how you would do it. Hopefully you did change the radical into a 1/2 power, but at this point you probably got stuck. Here's how this one works. This 5 has a 1 power. This 5 has 1/2 power. And what we learned back in Unit 8 is that anytime you have two exponential functions with the same base, you can add their exponents. So if you add 1 and 1/2 together, you're going to get 3 halves. And now these two things match, they cancel, and you're left with 3 halves. Final answer. So that would just be making you think, but hopefully you got at least 1 and 2 correct. If you didn't get 3. If you did get 3, nice job. Good thinking. All right, let's go ahead and take a look at our next part, the common log. What is a common log? As I told you, we're going to talk about two special types of logs today. One's called the common log. The other one's called the natural log. So let's talk about the common log. What is a common log? A common log is a logarithm with a base of 10. Logarithms with a base of 10 typically don't write the base. So I'll show you what I mean by that. Log x equals y. You'll notice that there's no little number down here by the g like usual. And when that happens, that's a base of 10. So when you guys see this, you can think of it like this. But really what we're supposed to write is this. But that's what it means. It's kind of like in other parts of math. Whenever you have like just an x, that means there's a 1 here and there's a 1 here. We just don't write it. Or if you have the square root of something, there's a 2 here, but technically we don't write it. Okay? So sometimes in math, we're so used to writing certain numbers that we just kind of get sick of writing. We say, oh, you know what? It's just so common. Let's not write it. We'll just know it's implied. So when you guys see log x, that means it's a base of 10. And there you go. Now, thinking of this in exponential form, right? It's 10 to the y power equals x. So thinking of it exponentially may come in handy. All right, let's go ahead and look at the same basic log properties. These are the same properties I showed you guys earlier. These guys. But I just rewrote them now with base 10. So what's log of 10? Well, remember, log with no base means the base is 10. Anytime this number matches this number, the answer is 1. Any logarithm, no matter what its base is, if there's a 1 here, equals 0. Log 10 to the x. Well, once again, if you imagine there being a little base here, these match, and you kind of think of them as canceling each other out, and you're left with x. Same thing here. This log has a 10 right here, so you can kind of think of these as canceling each other out, and it leaves you with x. Okay? And log base 10 is just like any other log. You can't have 0 or a negative number, so these two problems are no solution problems. Okay? So knowing all that, let's go ahead and take a look at some things that we can do here with log base 10, or the common log. So the first thing it asks us to do, it says use your calculator to find log 20. So we're going to find the button on our calculator that says log, L-O-G, and then we're going to put 20 in there. And then we're going to push enter. And there's the answer. So let's go ahead and write that down. And you guys might think, well, whoopity-doo, what's the big deal there? I will show you why we're doing that in the next part of this problem. This next thing says verify your solution by writing it in exponential form. So my base is 10, right? So this is going to be 10 raised to this power equals 20. So let's see if that's true on our calculator here. Is it true that 10 raised to the power of 1.301 equals 20? Notice it's not 20, but it's really, really close, and that's because I had to round it. Okay, and so it is good. We've checked it. It makes sense. So log of 20 is equal to 1.301. Another way of thinking about that is 10 to the 1.301 power is 20. Okay, so that is the significance of it. I wanted you guys to be able to see what this means. Log of 20 is the exponent that you'd have to raise 10 to in order to get 20. All right, now let's evaluate this expression by thinking logarithmically. Okay, what do I mean by thinking logarithmically? You can write this if you want to, but you don't have to. But what I mean is, do you guys see how there's no little base here? That means it's a base 10, right? So 10, or to what power would I have to raise 10 to in order to get 1 over 10? So what power would you have to raise 10 to in order to get 1/10? Well, 1 over 10 is the same thing as 10 to the negative 1, right? And so the answer, if we're just going to think about it logarithmically, is negative 1. All right. Now let's evaluate the rest of these problems down here using our properties. I'm going to do A and C first. I think those are easier. And then I'll do B last. So log base 10, notice there's no base, but that means it's 10, right? Log base 10 of 10, well, those are going to cancel and leave me with 3. Or here, this log doesn't have a base on it, so that means it's 10. So these cancel each other out and leaves me with the answer of 4. So those ones are nice and simple. Let's take a look at this guy, though. What do we do about this situation? Well, we've done this earlier, last lesson. You take the number that they give you, which is 1, and you put it over whatever number place it's in. This is the tenths, hundredths, thousandths. So this is 1,000th. So I'm going to start by rewriting this logarithm like this then. The next thing I'm going to do is I'm going to rewrite it because I don't like fractions there, right? So I'm going to rewrite it so that it's 1,000 to the negative 1 power. Next, I want this base to match my base. Now, what is my base again? It's 10 because we're doing natural logs. I'm sorry, common logs. So I need this to be a 10. And sure enough, 10 to the third power is 1,000. So I can just change the 1,000 into a 10 to the third power. Then I can multiply these exponents together. And now finally I can use property number, I think it was 3. And these cancel out and leave me with just -3. And there you go. Okay, so first thing I did was I changed it to a fraction. Then I changed the fraction to a whole number with a negative power. Then I made the bases match, and voila, we've got our answer. All right, so let's go ahead and throw one of these at you guys now. Go ahead and pause the video and try to do these problems. When you unpause it, you will see the solutions. Okay, so for 1a, if you type log 5 in your calculator, you should get 0.699. Writing that in exponential form then, it's 10 to this power equals 5, so that would be this. And if you can check that on your calculator, you should have gotten something really close to 5. And that proves that, yes, it's true. Next, number 2, evaluate this expression by thinking logarithmically. So hopefully you guys know that the cube root of 10 is the same thing as 10 to the 1/3 power. And so what power would you have to raise 10 to in order to get the cube root of 10? It would be a 1/3 power. Let's go ahead and take a look at 3a. This one I would just think about it logarithmically again. 10 to what power is 10,000? Well, that'd be 4. And I don't know if you guys are noticing this, but basically when it comes to common logs, if you have like, a 1 with some zeros after it, the answer will always be however many zeros there are. If there's 4 zeros, that's the answer. So let's go ahead and take a look at part B here. So you guys know that 10 is a half power, right? And since it's in the denominator, we're going to move it up the top and make it a negative half power. So 10 to what power would be 10 to the negative half power? It would be negative half. Last one, the cube root of 100. First of all, I would change that to a 1/3 power. Then I would change the 100 into a base of 10 so it matches my log base. And then I would multiply my exponents to get 2/3, and then we can use property 3 to cancel these out and be left with 2/3. So there is that. And that's working with the special logarithm known as the common log. Let's look at one more and talk about the natural logarithm. A natural logarithm is a log with a base of e. Okay? Logarithms also are written in a special way. We write them with simply the letters ln. So for instance, ln of x equals y, what that really means is log base e of x equals y. Okay, but this is how we're going to write it, but you can think of it this way if it's helpful to you. Now, since I'm thinking of it here in this way, we can write this in exponential form as e to the y power equals x. Okay, so here's how we'll write it. This is what it means, and this is how you'd write it in exponential form. All right, so revisiting our rules. Since this is ln, this is a base of e. And when these two things match, the answer is 1. No matter what your log base is, if there's a 1 here, the answer is 0. ln has a base of e, and anytime this base matches this base, they cancel each other out and leave you with x. Same thing here. And just like on the other ones, the argument cannot be 0 or negative, so these are no solutioners. Okay, so it's the same exact properties, they just look a lot different, okay? And that's because they're using different notation, but it means the same thing. So let's do example 5. All right, example 5 says use your calculator to find ln of 10. So we want to find our ln button, which is right here, ln, and then we put 10 in there, and equals. So we get about 2.303. So we'll go ahead and write that down, 2.303. Now, I want to write this in exponential form to verify this solution. So I want you guys to understand what I just found here. First of all, ln of 10 equals 2.33. Another way you could write that, although you shouldn't write it like this, but you can if it helps you think. ln means log base e, right? So log base e of 10 equals 2.303. So in exponential form, this would be e to the power of this equals 10. So e to the power of 2.303 equals 10. And we could check that on the calculator here to make sure that that's true. So let's find our e button. We're going to do second e to the power of 2.303. And it should be something really close to 10, and sure enough it is. So what are we finding when we say ln of 10? Well, when I find ln of 10, what I'm finding is I'm finding the power that I would have to raise e to in order to get 10. Okay. All right, so let's go ahead and do number 2. Use the properties of logarithms to evaluate each expression. So when you have ln here and e here, those are opposites, so they cancel each other out. That is property number 3. And so the answer is 4. Think about this one logarithmically. E raised to what power would you give you the square root? Well, the square root is just another way of saying a half power. So e to what power is the square root of e? Well, the answer is a half. Let's go ahead and take a look at this one. Perhaps you guys recall that we don't like fractions, right? So I'm going to move that e squared up to the top now with a negative power. These cancel, and I'm left with -2. Okay. So that is applying the properties of logs, but doing it with natural logarithms. All right. So why don't you guys go ahead and pause the video here, give these 2 problems a try, and when you unpause it, you will see the solutions. All right. So using your calculator to find ln of 50, we get this, but what does that mean? That means that e to that power should give us this number here, which is 50. And you can check these things on your calculators. ln of 50 is this on your calculator, and also e to this power is approximately 50. Okay. On this one, anytime you've got a log with a 1 here, the answer is 0. On this one, this is property 4, where this base matches this base, because this ln is base e, leaving us with 8. For this one, we don't like fractions of square roots, so I changed the square root to a half power. I don't like this being a fraction, so I move the half to the top and make the power a negative. And now using property 3, the fact that this base matches this base, those kind of cancel each other out and left you with -half is the final answer there. All right, and so there you guys have it. We've got lots of log properties. We're learning how to think logarithmically, and we've done so with various logs, and especially with those 2 special logs, common logs and natural logs. So, till next time, we'll see you guys in class. Bye-bye.